And now we will begin the third part of our 29th lecture in MAT353. So we're going to continue with the topic of vector functions, but now we're going to consider how calculus works in the context of vector functions. So most of the stuff that we will do here, the big picture, the punchline is that most everything is going to work component-wise. So when a vector valued function is just three functions glued together, and you want to take the derivative of that vector valued function, you're just going to take the derivative of those three component functions and keep them glued together in the vector notation. That's the big picture. So we'll run through this quickly. Limits for vector valued functions: if r hat is little f little g, so this is a function from r into r2, then the limit of r hat as t goes to t naught is going to be the vector given by the limit of the first component function as t goes to t naught together with the limit of the second component function as t goes to t naught, assuming that these two limits exist. If one or both limit failed to exist on the right, then the limit of r hat would not exist. So to take limits of vector valued functions, you just take the limits of the respective component functions. Scalar valued component functions. And there would be a similar definition if r hat mapped r to r3. You would just have a third limit here of the h of t function. With limits defined, we can define continuity. Really, I'm cheating here a little bit. The definition of continuity is that the limit as t goes to t naught of r hat is equal to r hat of t naught, just like the definition for continuity of a scalar valued function. But I'm leapfrogging that just a bit here, and I'm going to go ahead and say that r hat is defined to be continuous if and only if its component functions are both continuous. That is true. There's oftentimes equivalent characterizations of an idea, and one of them turns out to be the definition, or one of them is assigned the role of the definition, and the other gets to take up the role of a theorem. And I am reversing it here just so that I don't have to state the definition. Instead, this will work for our purposes. I don't have to state the usual definition. So we're going to call a vector valued function continuous if and only if each of its component functions is continuous in the usual sense. And again, it's stated here for a function into R2, but it would work just as well for a function into R3. You'd have three component functions that needed to be continuous before you could speak of your vector function as continuous. Derivatives for vector valued functions. There is a limit definition of the derivative. It is in the book in chapter 13. I'm going to go ahead and leapfrog that as well and just give you the practicals of how you compute derivatives of vector valued functions, which is, as we mentioned at the beginning of this part of this lecture, you just take the derivatives component-wise. So the derivative of r prime, or the derivative of r hat, is given by f prime g prime together in a vector. You go through and you take the derivative of each of the component functions and you keep them together in a vector in this way. Now let's have an example. So I'm going to take the helix that we considered a moment ago, or rather in the second part of today's lecture, and we're going to find its derivative. So r prime of t, I'm just going to take the derivative of t with respect to t, which is 1. The derivative of cosine t with respect to t is negative sine t, and the derivative of sine t is cosine t. So I'm just taking each of the component functions and taking the respective derivatives as I walk down the line here. And my interval for t remains the same. So that's r hat of t, this is r prime of t. Calculus works component-wise, or at least differential calculus is working component-wise for us so far. We will shortly see that integral calculus also works component-wise. So I have found r hat prime. What does it mean? Why should I care about such a thing? And the answer is that r hat prime is going to be the tangent vector / the velocity vector associated with the position vector r hat of t. So if r hat of t is giving you your position in Rn, as it has in the pictures that we've drawn so far, there's a curve in space, and r hat of t gives us a position along that curve that moves as we let t increase. So if we're thinking of r hat that way, as being the position of the bead on the string that is our curve c that's being described, then its derivative is the velocity of that bead. So in particular, r hat prime points in the direction of instantaneous motion of a particle having position r hat. So if r hat is the position, again, here's my curve C here, and you can imagine a bead on this string that's going to move left to right or right to left, depending on the parameterization. But here it's moving left to right, so if I've got a bead moving, r hat is always my position. So r hat of t with its tail at the origin, its head touches a point on the curve, and that's the position. For some t2 that's slightly larger than t here, our bead has moved along and is now at that position. So if r hat is giving you position on the curve in this way, then r hat prime is giving you the instantaneous rate of change of that position, which is to say it points in a direction which is tangent to the position curve. So right here, just at this moment, as my bead is passing through this point here, its instantaneous rate of change is off in that direction, and likewise down here. So the direction of the derivative is always tangential to the curve itself, which is intuitively reasonable to us. We've been thinking about derivatives as being tangent lines for some time. In Calc 1, we interpret derivatives as the slope of tangent lines, and something similar is happening here. There's a connection between the tangential direction associated with the curve and the derivative. So that's what the direction of r hat prime tells us. The magnitude of r hat prime also gives us information. In particular, it's the speed. So if my bead, quote unquote, on the t-axis is moving with speed 1, how fast is the corresponding bead on the curve C moving? And the answer to that question is given by the magnitude of the derivative. So here on this curve, if I had a parameterization of this curve such that the bead whipped along very quickly from left to right here, then I would see my tangent vectors, or my derivative vectors, would always be tangent to the curve, but they would also be relatively long, which would indicate how quickly the bead is moving as it moves along this curve. If I take another parameterization, multiple parameterizations of the same curve are possible. If I took another parameterization of this curve, but one in which the bead moves more slowly along the curve, then at every point we would have tangent vectors that pointed in the same direction that they did before. They would remain tangential to the position curve, but they would be short vectors now, indicating the slow motion of the bead along the curve. So r hat prime is a vector. Vectors have direction and magnitude. The direction shows you the instantaneous rate of the instantaneous rate of change, which is to say the tangent vector to the curve, the position curve, whereas the magnitude of r hat prime is speed, in the sense that if I have a bead moving along the curve, how quickly is that bead actually moving? Alright, let's have you folks think about a sample problem here. I would like for you to consider the circle of radius 3 centered at the origin. I want you to show me that the position along that circle, at the points on that circle, is everywhere perpendicular to the velocity associated with movement around the circle. So if you take position points on the circle, you're letting your position point move around the circle in a counterclockwise way, which should have been said here. So we're going to take movement in the counterclockwise direction. So I've got a bead on this circle that's going to move counterclockwise around the circle. I want you to show me that the position vector that represents the actual location of that bead is everywhere perpendicular to the velocity vector, which describes the instantaneous rate of change of the position of that bead. So give that some thought. We have talked about parameterizations from circles, we've talked about position, we've talked about velocity. Try to put those ideas together and show me that position is perpendicular to velocity for circular motion. Alright, that should have been plenty of time to pause the video and think about that problem. So we will have a look at a solution now. So I'm talking about I'm talking about movement along a circle of radius 3 centered at the origin. The circle of radius 3 centered at the origin is given by this parameterization. R hat of t is going to be 3 cosine t, 3 sine t, where t is allowed to go from 0 to 2 pi. So this is the parameterization that we discussed when we discussed parameterizations of circles generally. This is a parameterization for a circle of radius 3 taken in the counterclockwise direction. I can find the velocity vector, so that's my position vector. That gives me position on the circle for all values of t, and some value of t corresponds to every point along the circle. I can find the velocity vector in a straightforward way just by taking component-wise derivatives. So the derivative of 3 cosine t is negative 3 sine t, the derivative of 3 sine t is 3 cosine t, and t is going from 0 to 2 pi. Now I have position, I have velocity, I've been asked to show that position is everywhere perpendicular to velocity. I show two vectors are perpendicular by showing that their dot product is 0. So I take r hat, I dot it with r hat prime, I write out the vectors here, and I see that I'm going to get -9 cosine t sine t plus 9 cosine t sine t, and that of course sums to 0. And oh drat, it looks like we've introduced another line into the page here, but the idea is that if I've got this circular motion going counterclockwise, this vector from the origin to a point on the circle, that's what my position vectors look like. And for every such position vector, the velocity, the actual instantaneous rate of change, the instantaneous direction of motion for that bead particle is always tangential to the circular motion. So here's the position, and there is the derivative, the velocity vector. And if I dot those, I get 0. Same over here. This is some t value between 0 and pi over 2. Here's some other value of t between pi over 2 and pi to give me those positions. So that's what that looks like for circular motion. Position is always perpendicular to velocity for circular motion. And I apologize for the introduced lines here. I will clean the scanner again after this lecture is recorded. So now we have considered differential calculus for vector valued functions. We are also going to consider integral calculus for vector valued functions. So if r hat is little f little g, and both of those functions are continuous, and is usually the case, continuity is actually more than is needed to be able to define integrals, but it serves to make a simple statement of the theorem, and so we prefer the simple statements here. So with f and g both continuous, then the integral of r hat from a to b with respect to t is just going to be found by taking the integrals of the component functions respectively and putting those results into a vector. So this is what it looks like for definite integrals, where we actually have limits of integration a and b. Similarly, we can take the indefinite integral of a vector valued function, and that just amounts to a vector made up of the indefinite integrals of both f and g, and we collect our two constants of integration together in the constant vector c hat here. So c hat for this formulation, where r hat is into r2, then c hat would likewise be a two-dimensional vector. You've got your constant from the first integral, and you've got your constant from the second integral there. And we define this similarly if r hat maps into 3 space instead, so that there's a third component function. You just end up with a third integral in both of these expressions for definite and for indefinite integrals. So the intuition is a bit trickier here for integrals. It's not as straightforward as thinking about position and velocity. Instead, integrals are sums. If you think back to the definition, Riemann sums are how integrals are built. So the integral of r hat of t, as t goes from a to b, is a kind of sum, where you're taking all of the output vectors for r hat of t when t takes all values between a and b, and you're adding up all of those possible output vectors in some way. Each of them gets scaled by your little delta t expression, which goes to 0 in the limit, but you are taking a kind of weighted sum of all of the output vectors associated with r hat. All integrals are weighted sums of this type, fundamentally. Here it's just a weighted sum of integrals instead of numbers. I'm sorry, a weighted sum of vectors instead of one of numbers, which makes it a bit unusual. So if this is my curve C here, looking like part of the circle or maybe part of a sine or cosine function, then I might have my r hat value at a. I let my parameter increase from a to some larger value, and I've got an r hat there, another r hat value, r hat value, r hat values, and then r hat value at b. So as t goes from a to b, my bead on the string is swinging around this curve in this way. There is a vector for each value of t between a and b. I've drawn in 6 or so of those vectors. When I take the integral of r hat from a to b, I'm taking all of those output vectors and I'm summing them up. So the ones that pointed over here to the right, or to the left rather, the degree to which they point to the left is counterbalanced by the degree to which this vector points to the right in this example. And so when I add them up, I just end up with a vector that points more or less straight up for this drawing. So it certainly doesn't always point in that direction. I'm just trying to give a sense that if I add all of these vectors together, then I ultimately end up with some vector that points up and is longer than any of these were individually. So that's the big picture intuition of what's going on when you are taking a definite integral of a vector valued function. All integrals are always weighted sums. If you've taken my probability and statistics courses, you've heard me talk a great deal about weighted sums in terms of expected value and variance, and that is connected to this idea because those concepts are defined in terms of integrals. But all integrals, it's always your integrand value, and then it's weighted by your little delta x or your delta t term or your delta v term or whatever it is in the appropriate context. And you add up all of those products, and you take the limit as the delta variable term goes to 0. So as your delta x or here your delta t expression goes to 0. And that's what we're doing here, but we're adding up a bunch of vectors multiplied by our little delta t expressions. All right. So let's have you do a sample problem. Here is a vector valued function from the reals into 3 space. Find for me the indefinite integral of that vector valued function. So go ahead and pause the video and work on that problem. All right. So the indefinite integral of this vector valued function is going to be given by a vector, and each of the components of that vector are going to be indefinite integrals of component functions from your integrand. So we're just taking the indefinite integral component-wise effectively. I had r hat of t, and now I'm going to take the integral inside and integrate each of the component functions of r hat. The first is a classic u-sub problem, which I've glossed over largely. The second is just a polynomial, so we're adding 1 to the exponent and inserting the appropriate coefficient so that things cancel nicely. And the third component is a classic integration by parts problem, which again I've glossed over a bit, but you can check me on. Really, if you're checking them, the easy way is to differentiate each and make sure you get back the original integrand, which is definitely what I do when I try to shorthand these things in this way. And it does work out. You should get back the original integrands when you take each of these derivatives. And then we've got a plus c hat, where here c hat is going to be a 3-dimensional constant vector. So I'm going to write it, I've got my same vector here, and then plus a plus b plus c, little c, which is a real number as opposed to this c hat, a 3-dimensional vector. So a was like the constant of integration from my first component integral, b is the constant of integration from the middle component when it was integrated, and c is the constant of integration for the third component function having been integrated. And that's how that works. So almost the whole of calculus for vector valued functions works component-wise. That's going to wrap up our abbreviated treatment of chapter 13, and our next lecture will embark on chapter 16, which is really the heart of our final topic, vector calculus, and we'll begin with a discussion of vector fields in the next lecture. These will be functions from Rn to Rn, completing our list that we saw in part 2 of today's lecture of all the different types of functions that we've studied in this course in terms of dimensionality of input and output. All right, I thank you folks. We will return in lecture 30.